In this lecture, we are going to find the area of the region inside the outer loop but outside the inner loop of the cardioid 2 plus 4 cosine theta. We will set up an integral formula in polar coordinates for the area. The region whose area we are going to find is the region that's shaded in blue. This region should not include the orange shaded region. The orange shaded region is inside the inner loop. For a region that is bounded by the graph of r equals r of theta, and the rays theta equals alpha, and theta equals beta, the area is equal to half times the integral from alpha to beta of the square of r of theta. This is assuming that alpha and beta are between 0 and 2 pi, with alpha less than beta. To get an idea on how to set up the integral or integrals for the area of the region, we extend radial lines from the origin outwards all the way to the outer loop. Observe that as the radial lines fan out, the radial lines sweep over the entire interior of the cardioid, including the portion that is inside the inner loop. We are supposed to exclude the interior of the inner loop from the area that we are looking for. Our strategy will be first to set up the area that is inside the outer loop. Then we set up the area for the interior of the inner loop. And finally, we subtract the inner loop area from the outer loop area. As is often the case with setting up definite integrals, finding the limits of integration is of prime importance. So we must find at what theta value each loop starts and at what theta value it completes the loop. Let's see how the curve is traced as theta goes from 0 to 2 pi. At theta equals 0, r is equal to 6. So the curve starts on the positive x-axis, 6 units from the origin. As theta increases, the curve is traced in a counterclockwise direction. R remains positive until the curve hits the origin when r is equal to 0. After approaching the origin from the second quadrant, the curve leaves the origin and enters the fourth quadrant. Then the curve enters the first quadrant and reaches the origin a second time. The curve then leaves the origin through the third quadrant. And returns to the point at x equals 6 on the x-axis when theta equals 2 pi. We can use the origin as the initial and terminal points for each loop. We just need to find the values of theta at the origin or when r is equal to 0. 0 equals 2 plus 4 cosine theta means that minus 1/2 equals cosine theta. The first positive value of theta that satisfies this equation is 2 pi over 3, an angle that we normally associate with the second quadrant. Let's examine the geometry behind theta equals 2 pi over 3 at r equals 0. One can prove as an exercise that the cardioid is actually tangent to the line through the origin and whose slope is exactly tangent to pi over 3. However, the viewer might find it strange to note that the curve is already entering the fourth quadrant through the origin, even though there are still some angles from theta equals 2 pi over 3 to theta equals pi, angles that we normally associate with the second quadrant. So what exactly is going on here? If theta is on the interval from 2 pi over 3 to pi, cosine theta is in fact strictly decreasing from minus 1/2 to minus 1. Therefore, minus 1/2 is greater than cosine theta. is greater than -1. We multiply this entire inequality by 4 and then add 2 to each component. So we have 0 is greater than 2 plus 4 cosine theta is greater than -2. So that r is negative when theta is greater than 2 pi over 3 but less than pi. Because r is negative for these values of theta, the points corresponding to these values of theta will not be in the second quadrant, but in the quadrant that is diagonally opposite across the origin from the second quadrant. And so the portion of the cardioid corresponding to the interval from 2 pi over 3 to pi is the lower half of the inner loop. The next value of theta when cosine theta equals -1/2, that is when the graph hits the origin again, is when theta equals 4 pi over 3. Just like the theta values between 2 pi over 3 and pi, if pi is less than theta is less than 4 pi over 3, then 0 is greater than 2 plus 4 cosine theta is greater than -2. And so the values of r for the values of theta strictly between pi and 4 pi over 3 will be negative. And so the portion of the cardioid corresponding to the theta interval from pi to 4 pi over 3 will not be in the third quadrant, but in the quadrant diagonally opposite across the origin from the third quadrant. This time we get the upper half of the inner loop of the cardioid. There is a similar geometry at the origin when theta equals 4 pi over 3, similar to when theta is equal to 2 pi over 3. There is a second tangent line at the origin. This time the slope of the tangent line is tangent 4 pi over 3. So for the inner loop, theta is between 2 pi over 3 and 4 pi over 3. So what about the outer loop? After completing the inner loop, the cardioid starts the outer loop at theta equals 4 pi over 3. It doesn't leave the outer loop until it reaches r equals 0 a third time. One can check that the third positive value of theta when -1/2 equals cosine theta is 2 pi over 3 plus 2 pi, or 8 pi over 3. Therefore, the theta interval for the outer loop is 4 pi over 3 to 8 pi over 3. We start the integral formulation for the area with half times the integral from 4 pi over 3 to 8 pi over 3 of the square of 2 plus 4 cosine theta. This integral quantity is equal to the entire area enclosed by the outer loop, and this will include the inner loop area. So we subtract the inner loop area from this integral quantity. The inner loop area is equal to half times the integral from 2 pi over 3 to 4 pi over 3 of the square of 2 plus 4 cosine theta. As an integration exercise, the viewer can check that this is equal to 12 times the square root of 3 plus 4 pi. This is approximately equal to 33.35.